Good afternoon. Thanks for coming to this IAS Distinguished Lecture by Professor Vanderlei Bagnato. I'm very pleased to introduce Professor Bagnato coming from the other side of the earth, the Brazil. And indeed, he's one of the pioneers in the modern atomic physics. So Professor Bagnato got his PhD at MIT 1987, and he continued his the research as a PI in University of São Paulo from 1993. Actually, he has a very renowned scholar in AMO physics because he is the first generation, actually first guy who developed the ultra cold atoms trapped in the magnetic trap. And after he started his group in Brazil, he will talk about the state of art, the research, so-called the quantum turbulence in the Bose-Einstein condensates, which is not classical. In the quantum, you can also imagine the turbulence phenomenon in this type of things. So because of all his achievement, he got a lot of awards. I cannot remember all of them, but I only remember he's the member of the Vatican Academy of Science and the National Academy of Science in the US, and there are quite many other awards he received. And I'm very pleased to introduce Professor Bagnato, and he will deliver a talk about his fantastic research going on in his institute. Just one more thing is, he's also the director of the Optics Center, which is called the CEPOF, which is the largest optics center in the South American region. Okay, welcome, Professor Bagnato.
But a word to come here and talk to you about some of the exciting things we're doing on cold atoms. And the idea here is very simple. We have a Bose condensate, and a Bose condensate, when it's a 3D Bose condensate, and I will explain to you what is a Bose condensate in a very brief one transparency. It is a superfluid. And if it is a superfluid, it's a quantum fluid where we can study many things. And people are doing that. Like here, you have experiments to study some phase transitions. And what I'm doing there in this drop of superfluid is try to introduce turbulence. And you may be thinking, why doing turbulence in the quantum world? And I'm going to try to explain this too. So I put a few transparencies, maybe a little more than what I'm going to talk about. And I didn't put a lot of calculation. So rather than explain to you models and things, I want to explain the phenomenon itself. So I will restrict myself to some results and motivation. Why we think this is a good system to understand the disorder in the quantum world, and what that helps in understanding disorder in general. So I am from the University of São Paulo. I have a quite large group. This is the people in my center. And we have a big mixture of people, colors, and everything. And we do more than atomic physics in this center. And we actually do atomic physics, we do biophotonics, and we do nanoplasmonics. So those are the three branches in this optical center. We are about 6 permanent faculties, and then we have, of course, a lot of collaborators from different parts that come and collaborate with us. But in a second range, we do a lot of science diffusion. Maybe we are the only physics center with a TV channel. You can go to the internet now and you can see lectures and movies about science and everything. So we take very serious the diffusion of science. We have a program of innovation. So we have to collaborate with companies. It's not an option for us. It's an obligation. Part of our money comes from companies. We have to have them together. And we do a lot of innovation with we call social responsibility. Everything I'm going to tell you is in your homepage. Today is very common where you're speaking, people are seeing what's your life and what actually you're seeing that's true. So everything is in my homepage, on the homepage of my center. But I will be speaking about quantum atoms, quantum fluids, and this is the group of the people in the laboratory of condensates. We have a few students, postdocs, researchers, and many collaboration from abroad. Some of the people from here, you may know, I don't know if you know, Tsubota from Osaka. He's one of the authorities in turbulence, and we collaborate with him. So everything starts with laboratories that you can visit here in Gilboom Laboratory. It's a optical table filled with optics. And at some point here, we are able to cool down the atoms to very low temperature and produce what we call Bose condensate. What is a Bose condensate? I see that there are a lot of students, so maybe worth to tell you a few words about. Oh, by the way, we have 3 Bose condensates, and one of them is dedicated to turbulence. The other of them is dedicated to a mixture of superfluids, and the other one is dedicated to thermodynamics. You may say, well, what are you going to do with thermodynamics in those systems? But this is very nice system that's not homogeneous. You have a heterogeneous situation. Density is not constant everywhere. And in this situation, thermodynamics has to be done with a little care. You either do local density approximation or you do global variables. And I go to the second option. I try to define variables that are global. So density is not good for me. What's good for me is potential that holds the atoms and things like this, and then I will try to do the thermodynamics in that sense. This is not what I'm going to speak about, but this is something on our concern. So a Bose condensate, as you may know, is a gas in a potential. So we hold the gas together. And as you know, as you cool down, you may reach a situation where the thermal energy is compatible with the levels of energy. In that case, all the Boltzmann type of distribution for a classical gas breaks down, and you have to go to the quantum statistics. You have to occupy those levels. And then the statistic of Bose-Einstein, if we are dealing with bosons, start to play a role. Or if they are fermions, the Fermi-Dirac statistics. And we start to occupy the quantum levels. As you know, in the quantum world, energy is quantized. It's discrete levels of energy. You cannot have any energy you want. And it turns out if you start to keep cooling your system down and down, eventually there is only one quantum level that contributes to the properties of your system. When you reach that situation, this is absolute zero of temperature for this system. Normally, we don't get there. We get in a situation where one of the quantum states contribute to the overall properties of your system in the same way of the rest of the states. So you have a single quantum state that determines properties. In this situation, we say that the system is quantum. Because it's like having this room, and then suddenly I cool down the gas, Eventually, all the particles get in a single quantum state. The spatial distribution is determined by whatever is the solution of the quantum problem. Those quantum waves cannot be anywhere. They have to be matching these boundary conditions. And then the properties of the system, the macroscopic properties of your system, that normally, depending on the statistical average of all the components, suddenly have a different weight for a single state. And then pressure and all those macroscopic properties are modified. And we have a phase transition. So we cool down the system. Eventually, we reach Bose-Einstein condensate. It's a famous transition. This topic already gave a Nobel Prize for many people in recent years, right? And normally you are looking a gas, you are looking a cloud of atoms, which somehow is a sum of the wave function square of all the possible quantum components. And suddenly there is one component that contributes more, and what you see is a peak that appears there, indication that we reach that condition. So this is my starting point, okay? I produce the Bose condensate, and then I have to do something with it. Bose condensation is a very nice topic because it can cover many, many fields. If you are a particle physicist, you may know that field theory, which is very important for you, you know, you speak about breaking symmetry, field theory and everything. This is an example of symmetry breaking, spontaneous symmetry breaking. In statistical mechanics, magnetism, lasers, because now we can have many components occupying a single mode. In a laser, you have many photons occupy a single mode. Here we have many atoms occupy a single mode of your potential, which is a single quantum level. Fluids, optics, condensed matter, like the one you're doing, right? Studying fermion system. And it turns out that it is a superfluid. And it is a superfluid, and people can put vortices on it. Interesting that when you have a superfluid and you put a rotation, you introduce vortices like you do in normal fluid, but here they are quantized. They are very special vortices because following quantum mechanics, atoms in rotation has to have integer number of h bar of angular momentum. So vortices are quantized. So they are very interesting objects. And if you can make vortices, well, why not make turbulence, right? If we make those vortices to react and do strange things, we can create a disorder in this quantum fluid. And then that's what we define as quantum turbulence. It's clear to everybody? Okay, so this is what we do. We go for, the idea was we go here because everything else is being covered, so let's see if we can do something on turbulence. And as you know, okay, so how can you generate vortices in a fluid? This is a quantum fluid. And if you steer a quantum fluid, instead of making a big vortice, you make tiny little vortices where atoms will have a h bar of angular momentum in those vortices. Okay? So normally the vortices, as you know from basic physics, if you have a rotation, if you have finite angular momentum, there is no mass at the center of the force. Right? So there is a hole in the superfluid, in the center of the rotation, okay? So this is actually a cloud of condensate. And then when we make when we introduce rotation, pop, a hole appears at the center. And the rotation has a special quantization, as I'm going to show to you. So this is what we do. Normally, this is the only equation I'm going to show to you. Because of quantum mechanics, the velocity field has to have a special integration. Like we learned the Bohr integration. Angular momentum has to be integer number of h bar. The integral of the velocity around the rotation has to be an integer number of h bar divided by m. And this is we call circulation of the velocity field. And then the vortices are quantized. You cannot have any number here. You have to have an integer number of this guy. So this is a consequence of quantum mechanics, which make, this is a condensate produced by Wolfgang Ketterle at MIT. He rotates his condensate, and a lot of tiny vortices punches out. And he makes a lattice of vortices, like a Brikosov lattices in superconductor. And that is something interesting because this vortex has a core, there is a hole in here, and the size of this hole is related to what we call the healing length. And the healing length depends on the inverse of the density. And this is a big advantage to work with those systems. This is a quantum fluid, The best quantum fluid we had so far was helium, below the lambda point. But now we have this guy. And this guy has a low density compared to helium. So the vortex is big. That's why we can see the vortices. In helium, the size of a vortex will be like angstroms. You cannot see by eyes. But here, we can see. Because the density is small, therefore the size is big. This is a big advantage from what we do. And my idea is not produce an order vortices like this, but to make a mess. To make the vortices to go bizarre, produce turbulence. You know, turbulence, as you know, is a challenge. It's one of the fields that we know very little, even though it's very important. And this is a phrase of somebody important. It's always good to give a phrase of somebody important because you get credibility, right? So Heisenberg said that this is important. And maybe sometime God will explain what's happened. I don't know if he met God and God explained to him, but we didn't find that out yet. So let me explain what is turbulence for you first. I know that you all know from undergraduate courses. When you have a normal fluid, you have a laminar flow, which means a very well-behaved lines of flow. You know, normally in fluid mechanics, we use the flow lines to visualize the flow, right? And then when you try to increase the flow, because of viscosity, there start to be some deviation from a laminar flow. And there are points where those flux lines cross. And that's when the problems start. If you have a portion of fluid, it comes here. When it gets to this point, it can go here or here. Oh, it can go to the both places. And then start to produce vortices. And then this became a big mess. And you want to make the liquid to flow, but it stays around, so you need more pressure to make the liquid to flow when it's turbulent. And normally, it's a very hard problem because the set of equations is complicated. This is the Navier-Stokes equations. And there are many nonlinear terms. It's very hard to know when that starts. Normally, we can't predict everything. It's so dependent on fluctuations of everything that we can't really predict how will be the behavior of the system. So we come with some empirical ways of describing the system. And one way is using those adimensional numbers. That this is the Reynolds number. That's the one that's mostly used for flow of liquids and everything. And, you know, it's very important. And we know very little about. Let me explain why turbulence is important in general. If I tell you that life could not exist without turbulence, you're going to say that I'm joking, right? But it's true. If there was no turbulence when you breathe, if it was a laminar flow is characterized by having zero velocity at the walls. There will be no exchange of anything. It's zero. Oxygen could not be exchanged if the air flows laminar in your lungs. So you see, you could not be a good machine of breathing. The body is the same, right? When the blood flows in the veins, it has to deliver ingredients to the cells and everything. And if it was not turbulence, it couldn't. It's very interesting in the brain. There are parts of the brain that the blood flow is turbulent and parts of the brain where the blood flow is laminar. Probably because some parts has to be quiet and some parts has to exchange a lot of oxygen. So, you know, we are all results of turbulence. You know that if there wasn't turbulence, we all be dead. Because turbulence is responsible for spread the dust and make sure that they don't stay close to the ground so we can have fresh air even though throwing a lot of garbage in the air. The atmosphere does a lot of turbulence and make sure this mix so some places will collect the dust and so on. Anyway, it's a very important phenomenon. If you look to the universe, it seems to be turbulence everywhere. When you look to the sky with amplification, you're always going to see a kind of rotation. There is nothing without rotation. There is nothing without turbulence. People are so crazy that they say that the universe is a superfluid, turbulent. And on the walls of the vortices is where mass precipitate. Don't ask me any question about this because I know very little about those models. But anyway, it seems to be very important classically. You know, if you ask a taxi driver, do you care about quantum turbulence? He's probably going to say no. What about turbulence in general? Say, yeah, when I fly in the airplane, that's shaky. But actually, understanding turbulence is a challenge. And we are fighting to understand what is the best system to understand better. Because in normal fluids, it's too complex. From Leonardo da Vinci, he has drawings of turbulence. So this has at least 400 years old. And we don't know a lot. If you go to the American Physics Society, turbulence is placed as one of the big challenges. Because if we understand, it means that we'll be able to solve some problems, maybe. Why we are going to the quantum fluids? Well, because, you know, we always learn in school that the quantum world is very organized, right? It has to be. Otherwise, molecules will be a mess. We know that they obey orbitals, only some directions. We know that there is only like two hands of lattice possibles in nature, the Bravais lattice. So we know that quantum mechanics organize the world. So it's nice to see when that organization is destroyed. But more than that, quantum fluids, because vortices are quantized, we can only have one type of rotation. The vortices are all equal in a superfluid, which is not the same in a regular fluid. Therefore, we believe that by having objects, that's the vortices that compose the turbulence, and they are all equal, is easier to understand. So this is our belief. But even though we don't even know how this turbulence relates to the classical world yet. But, you know, we have to study, and then we're going to find that out. So Feynman said that, well, if you put vortices in a superfluid, they're going to tangle, and they're going to produce turbulence. And this should obey the laws, universal laws of disorder. And this is what I'm looking to study. Study the turbulence in a drop of superfluid, which is more like this, with a few vortices, and try to understand what kind of rules comes out. This is in helium, this is kind of old. In Bose condensate is new. And I could make a parallel for you why classical turbulence is interesting, and we know very little. Everything we know is empirical. From fundamental, there are a lot of numerical simulation. Computers maybe understand better turbulence than man today. But this is not the goal, right? We have to have control on this. Helium, which is a system that has been used to study turbulence for quite a while. You know, there are many groups around the world studying turbulence in superfluid helium. And why I believe that this is nice. You know, here we can control many things. Interaction between atoms. We can change dimension. We can do a one-dimension fluid, 2D, 3D. We can see how that plays, how increasing the phase space help us to understand or make it harder. We can do all kinds of things here. And more than that, here I'm going to show to you that I can produce turbulence with 20 vortices, which I cannot do in helium. Okay, and there are many other things we can do. I'm not going to have time to speak about all, but mixture of superfluids. We believe that putting two superfluids together, we can produce turbulence in one and start to turn on the interaction, and the turbulence migrates to the second fluid, and then we have a kind of extra knob to control things. And normally when you want to understand a phenomenon, you have to have knobs, right? to increase, decrease things, so you can understand. So this is our hope. And this is still a very beginning topic. I think I count that recently there are like 15 groups around the world start to worry about this. And many people worry about 2D system because it's easier. And I worry about 3D system because I want to get closer to the real life. There are many theoreticians, and normally this is a sequence. We punch vortices, suddenly they start to react, producing what we call a cascade. Energy start to flow, and then we start to analyze what's happened. Well, this is a sequence of papers that are being published from 2009. The ones in red is the ones that are coming out now. And I hope I'll be able to at least speak to you about matter wave aspects to show that superfluid turbulence is like a speckle in laser fields in terms of wavenet. That is something that's universal in turbulence. Turbulence is a hard problem because it involves many scales. When you produce turbulence in a room, it's important the size of the room, the mass of air is here, but also it's important the size of the molecule. You have to go from the macro part to the micro part. All the scales are important. And the way that happens is, normally you introduce energy in a large scale. I get a big piece of wood and I start to shake it here. The air will produce turbulence. This is large scale. But that energy starts to go to small scales and flow until reach the size of atoms and things, which will be like vibrations or phonons or heat. Okay? So involves many scales. Normally, the way that the energy flows from one large scale to small, we call cascade. And there are a few models. One is the Richardson cascade. We believe if vortices make rings and rings react, makes tiny rings in it. Go to the lower. Or Kelvin cascade, which is you have a vortices, they start to react to each other, they start to wiggle, we make waves on the vortices, and that goes and goes and goes until reach the size of phonons, and then dissipate like sound. And this is the main mechanism in quantum fluids, we believe. Okay, so let's start with the condensate, how we introduce vortices in this. I do what I call a washing machine for atoms. I put my atoms in a trap and I start to shake like this. Like in a, if you get a cup of coffee and you start to go this way, nothing happens. If you start to shake that way, drops will spill out. So energy goes from your motion to tiny little scale, and then a lot of energy gets in a drop and it drops out, right? It's easy to generate turbulence that way. And this is what I do in my superfluid. I start to move, so I produce my condensate, I start to shake, and then vortices start to appear, and then I shake harder, and I go to turbulence, and then I analyze what's happened. So normally I have to prove that everything I'm doing is fine, and if I produce vortices like all the same, they crystallize. You know, this is Abrikosov got prizes for that, right? So this is they interact, they are like tiny objects, they crystallize. I have to produce vortices, anti-vortices, and in many directions so they can react. So I have proved that we make vortices, anti-vortices, clusters of vortices and everything. This was long ago. And then once I start to produce vortices, a lot of vortices react, produce a turbulent cloud, and then something else will evolve. Because in this superfluid, they start to react, and they evolve to a state of very big fluctuations of density that we call wavy turbulence, which we believe is the final stage of this disorder in the superfluid. Okay, so for you to understand what's happened, let's take a drop of superfluid, 1 million atoms of rubidium, temperature about 70 nanokelvin, about 70% condensate, and I start to excite in this shaking, rotation, tiny little everything. first of all, they start to bend. This is called Scissor Modes, which is a consequence of superfluidity. And then vortices start to appear. And then turbulence develop. And then eventually, because this is a quantum object, I put so much disorder that the phases start to be random distributed on this drop. And the system breaks in tiny little islands. This is also common to superconductor. When you produce a lot of impurities in superconductor, high TC superconductor, you break the superconductivity at long range and only became superconductor in a short range. It's about the same. You create drops of superfluidity. And we've been studying this. Everything is like putting a diagram to make clear. This is amplitude of excitation, time of excitation, and this diagram resumes more or less everything that can be observed. And we've been studying this for a long time. It's very nice to know how turbulence is formed. So this is the number of vortices growing as a function of my time that I excite. I keep exciting, number of vortices grow and then change. Because the system is a drop, I cannot put more some number of vortices. So I saturate with vortices and then they start to react. And if you go in another amplitude of excitation, sorry, after the saturation, vortices disappear. And they disappear, giving place to another type of phase, which you believe is the weak turbulence. So this is how the things evolve. Now, there is something very interesting here. If you have, suppose I have a gas in here. Okay, so before I explain this, suppose I have a Mickey Mouse balloon. Everybody knows what's a Mickey Mouse balloon. And I blow, there is a gas inside which has the shape of the Mickey Mouse head, right? Now I'm going to blow the balloon, boom. The gas is going to expand. Can you guys detecting the gas tell me that this is a Mickey Mouse balloon? If it is a classical gas, I will say no. Because it starts to spread and goes uniformly spreading, okay? Because in each point you have a maximal Boltzmann distribution. It goes everywhere, the same. You lose the information about the shape. Let's say that we have inside the Mickey Mouse balloon a superfluid. Okay? And then I blow, boom. You know, because it is a superfluid, the gas has to be seen like a wave in propagation. And you know, whatever the wave is more squeezed, will diffract more. So the ears of the Mickey Mouse will go faster, will diffract faster. The head will diffract less. But if you're smart enough, you can calculate and come back and say, oh, that's a Mickey Mouse head. Now, suppose we have inside the Mickey Mouse balloon, this is getting too long, right? Okay, suppose you have inside the Mickey Mouse balloon a turbulent superfluid. And then I blow, boom. You know, doesn't matter how long you wait, always going to be a Mickey Mouse head. Interesting. This is what we call self-similar expansion. It happens with a superfluid gas in expansion. And this is here. This is a classical gas expanding, thermal gas, near the condensation. You know, you squeeze it that way, but you let it expand, it turns to, we divided the two directions, we call aspect ratio, and turns to 1. Doesn't matter what you do. If it is a condensate, it happens like a laser. Whatever you squeeze more, it diffracts more. So that is an inversion of the aspect ratio. Now, if it is a turbulent, it stays the same. Incredible. And this, I think, we explained today based on the dynamic of the superfluid, turbulent superfluid. Well, there are some simulations that proves this too. Okay, now, if you want to speak to anybody about turbulence, the only thing they care is about spectrum. Give me the spectrum of energy, which is how the energy depends on the momentum. So, and then the only thing they know is what they call Kolmogorov law. there is a region here that the energy depends on the momentum to the minus 5/30. This is a law that was discovered by Kolmogorov doing analysis, the dimensional analysis of the problem. And once that happens, we can prove that energy is flowing from large scale to small scale, which is a proof of some turbulent phenomena going on. You understand me? Okay. So, if you want to show that you have some turbulence, you have to come with a spectrum. And people spend their life measuring that in turbulent helium and everything. And most part of the people spend their time showing that if there is any equivalence to the classical fluid, any fluid you take, any turbulence you take has this law. In a range of momentum that's called inertial range. It's the range of momentum where energy is not dissipating, it's only migrating. So it's a cascade. It's clear? Okay, so we're gonna measure this. But to measure this is not so trivial. But luckily, when I produce a turbulent Bose condensate, it is a kinetic dominant state. Most of the energy is kinetic, is in momentum, it's not in interaction. Then you can guess what I'm going to do. What I'm going to do is scatter neutrons from that to get momentum. No. I let expand. If I have a cloud that's only depending on momentum, when I let expand, I can measure what is the number of atoms with each momentum class, which is the occupation of momentum. And from there, multiply by k squared, which is the energy, I have the spectrum. So this is what we do. And luckily for condensates turbulent, they are kinetic dominant states. We can prove this. Therefore, by let expanding, we can measure. But there is another way, and if there is any astrophysicist here, it's called the power spectrum. When I look in the momentum space, fluctuations is what give you the energy. And people in astrophysics, they see these clouds and everything. By doing statistics of that, they measure the momentum, the spectrum. How is the energy distributing that stuff? Then they can decide if the cloud is a new star or if it's an old star or whatever is the evolution. And this is what I'm going to apply for my condensate. Get the power spectrum by doing statistics of the expansion. Everything has to be done in momentum space. Okay? So we're going to do two different measurements now. Measuring the momentum distribution or measuring the power spectrum. How we do the momentum distribution? Okay, we get the cloud. This is how a turbulent cloud looks like. You see? It's like the Himalaya, filled with holes and valleys and everything. And we let expand. And then I see, the atoms with less momentum will not go very far. The atoms with higher momentum will go very far. So by sampling the number of atoms that goes in a time of flight type of measurement, I can do a transformation, which I'm not going to bother with that, because I measure in the plane, I do absorption of light to measure this, and then I have to use symmetry and recover the 3D aspect of it. And when I do this, I can get the momentum distribution. This is the momentum distribution. So this is the momentum distribution for a few atoms, a few vortices in the cloud, and this is when it's turbulent. And you can see here that already start to appear. First of all, atoms migrate to lower momentum to higher momentum, which means going from large scale to small scale. Momentum normally goes opposite to space. The energy, large momentum, needs small space, small scale. Right? It's the reciprocal. And then we measure this, and we found a power law. Here it is, in a more clear way when you do the transformation. And we found something that has nothing to do with Kolmogorov. So for this system, we believe it's turbulent. It's not minus 5/30, it's minus 3. And then recently, people from England measured the same in a Nature that was published about 6 months ago. And they measured the same minus 3. Okay, well, Well, we demonstrated that actually as the time goes, energy puts in higher momentum. So you see the momentum distribution evolving. So we can calculate. And now we're going to measure in a different way, with power spectrum. Power spectrum, we take a picture, many pictures, and do a statistic of the fluctuations. This is a technique that's well applied for many areas of physics. And when you do that, you can prove that by doing the correlation of those statistics in the density correlation, you can do the Fourier transform, and this is the power spectrum. So we have done this. Sorry, you're not going to bother about this. And then we find in a more clear way all the momentum variation, all the momentum spectrum, or the occupation here, and we see the power law. So what this means that we prove there is cascade. There is turbulence in this sample. And is a type of turbulence characterized by a kind of power law. And from this power law, we can more or less understand what type of turbulence we have. Okay, so this is a very interesting thing because depending on the coefficient of the power of the spectrum, if you have the occupation number, each atom has h bar square k square divided by a 2m of energy. So you multiply by k square if you get the momentum occupation by expansion. So you can get the energy, or by doing the power spectrum, the correlation, density-density correlation, you directly get this. And they both agree as well. What is the coefficient? And this dependence on the energy spectrum tells us what kind of turbulence we have. And in fact, the turbulence we have is called wavy turbulence. What is wave turbulence? Well, but you start with vortices. I know, but they react so much that at the end, this cloud has big fluctuations of density. That's what ends. And maybe cannot be considered as a single quantum object anymore because the phase is random distributed. And this is a way to characterize this turbulence. So this is what everybody that's measuring is seen as an end of stage of the turbulence in the superfluid. And well, then I am now trying to understand how the system evolved to this stage. And I cannot explain deep, but you see, this is a regular drop of superfluid, and as the turbulence is established, this power law starts to develop until reach this situation that characterize a final developed state of turbulence, which we believe is the weak turbulence. And well, there are many diagrams we can do. In helium, they never observed this, which is the return. If I keep pumping more energy to my turbulent, it doesn't stop there. It starts to come back to something. And this we don't know what it is yet. But we know that here something funny has happened in this stage, and we are now investigating this. If you're talking about turbulence, maybe it's nice to calculate entropy, disorder, or a function that characterizes the disorder. We normally use what they call the Shannon Entropy, which is an entropy they use also in quantum computation and communication, and quantum information in general, which is basically this definition. If you know the density, the integration gives you the entropy. And as you can see, you start to excite your system, and suddenly, when it builds up entropy enough to evolve to a disorder, it does. So then the entropy starts to grow. Until this point here, if you stop, the system returns. We didn't build up enough entropy for the system to be disordered, to be a turbulent one. So we are characterizing this. I'm going to jump to this because I excite and I stop, and the entropy starts this evolution, this reaction of vortices taking the system to a turbulent regime continues to grow even if the excitation is turned off. It's like, that's different. In a normal fluid, if you stop to excite, the turbulence decay. But here, no, it's keep evolving because there is no dissipation. The system has to evolve until it reaches phonons. Sound is the way to be dissipated in the quantum world, in the quantum fluid. Okay, we believe that is when I start to excite, this is an equilibrated condensate. There are a sequence of stages for the disorder to be built up in the quantum fluid. And we are characterizing this, using different things. Fresnel number, which, as you know, Fresnel number is a number that using optics to characterize disorder in the optical field we want to use as well. Or Mach number. Mach number is the one related to the speed of sound, which also use it to characterize this turbulence. And we'll be trying to characterize that way, but we've been not well succeed. This is the real measurement of the evolution of the whole energy distribution. And we have to come up with an equivalent temperature for the system that's complete out of equilibrium. So we don't know yet how to define this, to define those numbers. Okay, now I want to change a little bit and explain to you turbulence in another point of view. What we have here is matter waves, right? Quantum fluid is a composition of de Broglie waves, matter waves. And when I let expand, I let those matter waves to expand. And normally, this is a normal condensate in expansion. That is an inversion ratio. So if I look at the dimensions, vertical and horizontal, one goes slower, then the other goes faster. Because of waves do that. Whatever is shorter, more localized, it's expand faster. It's called diffraction, right? Now, this is the turbulent one. We saw that it keeps the aspect ratio, doesn't change. So what applied there doesn't apply here. But those are waves. There is a situation in optics that happens that. Lasers. Laser is a guy that when you try to squeeze it, it diffracts. Right? Diffraction limit type of thing and so on. But if you have a lot of random amplitudes, if you scatter a coherent laser in a rough surface, you produce what they call speckle field. Speckle is a composition of random amplitudes and random phases. So people define as a addition of complex fields with random amplitude and random phases. And if you look at the expansion of a speckle beam, it behaves exactly like our turbulent condensate. And why? I'm going to explain to you. When you have a coherent wave, the diffraction, the expansion, depends on the wavelength divided by the size. If you learn about Gaussian beams, if you try to focus a laser beam, when you tie to this, it diffracts more. So this is what governs the propagation of a coherent wave. Now, when you have a disorder, the diffraction angle depends on the wavelength divided by the coherent length. Depending on the size of those coherents. What is the coherent domain? And this, of course, may not depend on the direction. Therefore, we expand equally in all directions. Especially if you are in what we call, this is the behavior, right? You see that the BC expansion and an optical beam propagation, they are very equivalent. They are both waves. A BC is a coherent wave. A turbulent BC is like a collection of coherent domains, like the speckle optical beam. Therefore, there is a big analogy. We measure correlation to prove that there was this is a paper coming out, I hope soon. We measure correlation to show that they are complete equivalent. Correlation is you measure there's an expression. You measure the density here and see how they correlated. This is called density-density correlation. Of course, for the light field, we call intensity-intensity correlation. And they are fully equivalent. We can prove that. And, this is, you don't care. Now, let me explain to you in a simple diagram why this thing happens. So when you have a turbulent cloud, you have little domains of coherence. And when they expand like this, right? Each domain follows the coherent expansion. That is the diffraction on this. But if you add up, because you have domains, you see that each domain in a short field, close to the Rayleigh range, we call in the optics, the domains expand all equal, and then you preserve the aspect ratio. It's like having 3 little globs in here, and they all grow equally. So this preserves the shape. And this is a consequence of the wave nature of the superfluid. So I think this proves that turbulent BEC is in expansion, right? Only expansion. Is like a speckle field. So this is something that we have to remember when people first made BEC. They said that a classical gas is for a normal light, what a BEC is for a laser. Many, many components using the same mode. So this is a proof that that's true, even though we didn't doubt. But this is a proof, even when you have a disorder. And I think this is merging quantum turbulence with statistical atom optics. Why you can use that for? I don't know if you are in statistical optics, but people want to have a 3D speckle field. Normally they have a 2D, right? A laser beam propagates, you take cross-section. That's where the speckle are. But here, it's expanding 3D. So it's a matter wave, it's not a light wave, but it's a 3D speckle example. And I think this has a lot to be explored. And, but this is in expansion. It's not exactly what I'm interested. I'm interested in what's happened when the gas is still confined, when the turbulence is developing. And this is what we're proceeding. Producing turbulence in classical and quantum world is a little different. If I take a glass of water and I produce a big vortex, I put a spoon there and let it go, that decays. In the quantum fluid, if I produce a giant vortex, this vortex decay in tiny little vortices. Because if you remember, the energy is the momentum, the angular momentum square divided by 2 times mr squared, right? That term there. So for the system, it's better to take a giant vortex with a lot of angular momentum and break in tiny little ones. That's why Wolfgang Ketterle produced he stirred the condensate, and then he sees a lot of tiny little ones. But now what's interesting is, in the quantum fluid, if I take a drop, I produce a giant vortex. This is a vortex with a circulation equals to 4, which means 4 h bar of angular momentum per atom. This system is metastable, will decay in 4 tiny little vortices. And here's a proof. This is a real experiment. This is a giant vortex in the condensate, big hole, and decay in 4 tiny little ones. But the problem is, when this decay, there is a big perturbation, and spontaneously the system goes to turbulence. So the quantum fluid is a system that maybe turbulence can be generated spontaneously. This is a very ordered system, but during the decay, you may create turbulence. And we've been studying this. This is the experiment. There is one paper already published and one in the archive. And this is, if I can do this, show to you, a simulation of 2 vortices of opposite n equals 2, of opposite sign. When they decay, they are decaying. Oh, that is a very nice way to decay. It's completely different from a classical fluid. Here, a giant vortex decay by winding and dewinding the elementary vortices, which is something unexpected. But then they evolve and they generate turbulence. So we believe that generating a giant vortex in a drop of condensate naturally, spontaneously, will go to turbulence. And this is what we're trying to produce now. Well, I think my time is basically over. We did some more experiment. It's very nice, those quantum fluids. This is a situation, I told you before in the very beginning that the system became turbulent. This is a single quantum object, macroscopic quantum object. Turbulence introduces phases, random phases everywhere. Each vortex has a phase around it. And when this start to react, it produces a mass of phase. And we all know that a quantum object is amplitude and phase. The condensate has a single phase to start with. And then I introduce a lot of phase, these breaking pieces. I told you that at the end of the turbulence, I create a kind of domains of phase, which is islands of superfluidity. So we did in Texas another experiment. Start with a 1D BEC. You cannot have vortex in here. But then we start to oscillate. Eventually, these breaking domains. And if this was a kind of classical fluid, I break in tiny little drops and I wait till they recombine. Here, they don't recombine. This is a quantum system. To recombine, they must have a mechanism to reorganize the phase, and they don't have it. So the system breaks and stay like this. And those are drops of coherent, and we have done a theory to explain, and these go beyond what we call mean field to explain. So we are building up theory for explaining this granulation we call, and I think it's very exciting. Everything I told you is in a paper we published recently. Those review papers is nice because you can combine in a very nice language everything about one field. So this is a physics report where we combine up to last year everything we knew. Now we have a lot of new things, but this is a good start if you want to understand a little bit about this quantum turbulence. And you see, what we started to see that was hard to see in other systems, in the quantum fluids, is this clear migration, clear cascade. And now we are producing an experiment that has two superfluids, where we believe we can suck vorticity in one, put in the other, and control, and try to understand how the things start, how it ends by controlling, having these two systems, where I can drop the turbulence in one or in the other, and try to understand. So I think it's a very interesting system to understand the turbulence in this quantum fluid. You may ask, what are we going to understand about turbulence in the real fluid, in the classical fluid? And I tell you, maybe by understanding here, we are now making models that allow us to predict where is the things going. Based in local equilibrium type of approach. And I hope very soon we will be able, by looking the phase space, by looking the momentum space, not in real space, we will be able to tell where the energy is migrating. So we'll be able to tell how the turbulence develop. And this is the very beginning, right? I think if we understand how energy flow, we can come with some equations or some laws that can tell you how is the system evolving more than in the empirical way, the way it is done now. So, and then maybe after that, we can go to classical fluids, which is the real interest. I understand, that's the real interest, but this is a situation that quantum world help us. Normally it's complicated. To see things in quantum objects, it's much harder to see in classical objects. Right? Today we were having lunch together and he said, no, it's much easier to study a glass of water than your condensate. And I agree. It's much easier, but maybe it's more easier to interpret it in my quantum system than in the classical. Classical is too complicated, this phenomenon, and we don't understand yet. Maybe in the quantum world, we already seeing things that we cannot follow in the classical. And that's a good indication that it is a promising system to understand the establishment of the disorder. And then eventually, we can see what's missing to really be able to understand it in the classical world. And well, I want to thank you for your attention. I hope it was not too heavy. It's a new topic in BEC. Things are starting now. More groups are getting involved. And if I was a young physicist, I will choose something that's very challenging, right? I know that's hard. We always balance, oh, I need to finish my PhD in 4 years. Here in Korea, 4, right? 5. I think, doesn't matter the distinction of time. You have to do something that is useful. That's not only one more thing, it's the thing to advance. We have, as a physicist, we have to learn to have courage to take challenges. Doing things that everybody knows does not help the way we think. Maybe we should risk and do the new things. And of course, this is not the only topic. In the quantum world, this is a many-body system, right? Many-body physics, people did a lot of theory. Only now we can experiment. I don't know how much of the theory will survive. But I can tell you that many-body quantum system understanding is quite robust in theory. But they do situations that they didn't predict. Now we can test. And now, system like this will allow you to understand how I evolve from a whole quantum macroscopic object to a classical macroscopic object. In between, I have to understand how everything is happening. And I think this is good. It's not the only challenge system, but it's one of them. And I see a lot of young students, so I hope if you don't understand the lecture, which I hope you do, you have done, I think you understand the final message that physics is important when we break challenges, when we have new additions for evolution of the understanding. Thank you very much, and if you have any question, I will be happy to solve. Thank you.
Thanks for great lectures. So any questions from audience?
Okay.
I didn't want to be...
Yes, priority.
No, you could give it to somebody else first.
No, go ahead.
No, because I had a comment and a question, kind of a comment and a question. So your expansion you showed goes asymmetric. It does slightly more rapidly in one dimension than the other dimension. 2 out of 3 you showed. And if you remember the Kolmogorof's, turbulence depends on the number of dimensions. So my guess is you don't necessarily get 5/3. You'll get some mixture of dimensions, kind of thing. But so I know the transition from 2 dimensions to 3 dimensions makes a power difference, and so that's just a minor point. So the question I have, I start with a comment, then I'll ask you the question, which is, I would disagree. If I'd been at lunch, I would have disagreed. I would think it's easier to understand the quantum system than the fluid system. And I think there's a basic difference, and this is what finally coming to the question, and that is when you think about the pure Bose-Einstein state before you introduce the turbulence, the vortex, it's essentially a completely entangled state. And in the glass of water, it's not entangled at all, right? There's no ground quantum state everybody's in. And you're introducing the vortices and having them cascade, and I would like to see if you made a prediction about how the entanglement went. But what I suspect is every vortex carries its own local entanglement, and you break the global entanglement up into small pieces. And the extreme limit of that would be the glass of water. Right? And so my question is, did he actually calculate the entanglement, or are you doing it because you're doing it either in momentum space or in real space, but it's essentially...
Yeah, we normally work in the momentum space because we care about momentum, and we cannot do in situ measurement. We had to wait this to expand, and by expansion, you already mapping the momentum. So naturally, we work in the momentum, but doesn't matter, right? Momentum, we learn in quantum mechanics that momentum, real space, is just connected by Fourier transform. Now, when I have a superfluid, all particles are in the same state, the same phase.
And they're entangled, right?
They're all there. Now, when I introduce rotation, the rotation belongs to everybody. The big problems start when I put those rotations and they start to react. they start to evolve. And those, you see, I have two vortices. When they come to the same point in space, if I had a blackboard or a whiteboard, is that okay? It just is, see, I have one vortice, emits another vortice. You know what's the result of this? Is two vortices. The one comes here, the other comes here. So I produce, and then those will react. So you can see that sooner this became a big mess, because the phase of one vortex has now to see the phase of the other, and then eventually I have so much reaction, and then rings start to form and everything. So a phase just cannot be handled anymore. And then I think we lose the long range correlation, the long range coherence. And then they are tangled, but very locally. Right? And then we lose all this aspect of combining things in the quantum many-body system. And then it's over. You can't recover that anymore. So we didn't calculate the entanglement because normally we use mean field. We have a single mode with a different number, which is about the same. But we didn't characterize this as losing the entanglement in some sense. But I think it could be done. Yeah. I don't know if I answer.
But you kind of have the same instincts I do. I just wondered whether you'd actually calculated and thought about it in those terms, because that's a different, it's sort of the more modern way people talk about.
Yeah, you see, I'm experimentalist, and I collaborate with some theoreticians. Some of them in England, some of them in Japan, some of them in Brazil. And people are doing a very nice, heavy many-body calculation for this. And so far, I didn't see anybody speaking about an entanglement type of analysis. But I will suggest to my collaborators if that could be a good view. You have a question?
Yeah, I'm interested in your spectrum in quantum system. And I find in Kolmogorov, we know the power is minus 5/3, but in your quantum system, the power may be minus 2.9. So
no, actually, it's -1 the spectrum. It's -3 on the momentum. It's -1.
Okay, so for this difference, any explanation for this?
Yeah, the explanation is that it's a completely different system. If you take Kolmogorov deduction, first he has to imagine a larger system because he needs symmetry. I have to come and say what kind of scaling I can do on the hydrodynamic equations that make it invariant. This is the principle of Kolmogorov. And then he changed the time, he changed the length and everything, and see that there is a law that the energy has to obey for that to be true. But in our case, it's a finite system, right? Tiny finite system. I don't have all that range that Kolmogorov can imagine. And I think the end of the thing, my turbulence evolves. Vortices cannot survive forever there in my drop. At the end, they disappear and they turn into big fluctuations of the density, which is called quantum wave turbulence. It's another type of turbulence that can exist. And what they didn't know that we could migrate from what they call hydrodynamic turbulence, which is this Feynman idea of tangle vortices, to big fluctuations of density, which is the weak or wave turbulence. And I think this is in those systems, this is what's happened. Now, what are the real mechanisms that takes place? This is what we want to measure, intermediate from going to vortices to wave turbulence. I think we're going to learn a lot if we do that. So, but there are very good theoreticians. Nazarenko is one of them that characterize very well the wave turbulence. And it gets in the spectrum, in the occupation number, -3, or in the spectrum -1. So we all agree on that. And many other people are doing experiments with condensates and get equivalent results. So it seems that we have to understand now how a hydrodynamic turbulence, that's one made with vortices, goes to big fluctuations of the density, which is the wave. And I think this is intrinsically related to the quantum nature of your system. And, but this is what we have to find now, this pathway between.
Okay, and another question is, any theoretical result or model for this quantum system?
Yeah, normally, normally, you see, there is an equation that governs those fluids. That's called Gross-Pitaevsky equation. Gross-Pitaevsky is an equation, is a nonlinear Schrödinger type of equation that governs those quantum fluids. And with that, we can predict a lot of the things we observe, but not all. It seems that we have to go beyond this approximation to explain all. And this is in the stage we are now, is trying to evolve the understanding of this, because we don't have a single mode. Once you start to be turbulent, probably it's not a single many-body state that's there. It's a superposition of states, many-body states, not single particle states. And this is what we have to now understand. But a lot of the things we do, people understand with simple mean field approximation, which is a Gross-Pitaevsky type equation. Okay. There are many things we're doing now. It's like, it's very interesting, you know, you produce this turbulence, and then the high momentum atoms, the ones that are gonna escape during the expansion, but they are a big wave. They look to that random core and they localize. This is like a localization or anomalous diffusion in the quantum system, which we are investigating now. And so each day in the lab is it seems to be a news. It's very hard to keep track of everything, and writing papers, and so. But it's a fantastic disorder in the quantum world. Is something that is not so old, I don't think, especially in the experimental sense. And we're going to learn a lot, I guess, in this system. I hope you agree. Okay.
Any other questions from audience?
Oh, you can ask how is the weather in Brazil if you.
Actually, you showed that you have several vertical systems. And actually, I saw you have one lithium natrium mixture EC system.
Yeah. No, we have a rubidium. We have a sodium potassium. Sodium potassium is a mixture.
Have you tried to make a turbulence in the mixture system?
Have you
tried to make a turbulence?
Oh yeah, that's what we're doing. I didn't have time to show everything, but what we're doing now is sodium potassium is nice system because there is an isotope of potassium, which has a very nice tuning interaction, sodium potassium. So the idea is there is no interaction, and we can steer the sodium, produce lattice, produce turbulence in the sodium, and then we turn on the interaction with potassium, and then vorticity should migrate. This is being simulated already. And if you suck vorticity, you're going to reverse the turbulence, or somehow something will happen there. All the angular momentum has to go to other fluid. And then I think it's a knob to control. The first thing we want to do is produce a tiny little potassium diluted in sodium. So we're going to fill it up the vortices of sodium with potassium. So we're going to produce turbulence in a massive vortice environment. This is different. And hopefully something nice will come. At least to see it will be easier, because now we can only find the potassium atoms. And we're going to know where are the vorticities, and when they disappear, when they diluted, when they make a big mass. So this will be a marker for some of the things we're doing. You know, at the moment where we are producing vortices in sodium and start to put the potassium. And then some people, you know, everybody gives a different idea, so we select the best ones and keep going to finish something, right?
Okay, and just one more questions. All right, if not, because of time, maybe let's thank Professor Bagnato again, and maybe we can continue the discussion outside the lecture.
Well, I thank you very much.